In this lesson, we're going to look at graphing to solve systems of linear inequalities. In the previous sections, what we've looked at is how to graph linear inequalities, also how to represent linear inequalities having to do with word problems, and then how to graph more than one linear inequality or systems of linear inequalities. What we're going to do in this lesson is look at word problems specific to linear inequalities and graphing more than one set of constraints. So a system of linear inequalities having to do with the word problem. So let's look at this first problem. It says, a company makes two types of boats on different assembly lines, aluminum fishing boats and fiberglass bow riders. When both assembly lines are running at full capacity, a maximum of 10 boats can be made in a day. The demand for fiberglass boats is greater than the demand for aluminum boats, so the company makes at least 2 more fiberglass boats than aluminum boats each day. What I've already done is highlighted the constraints. There's two separate kind of limitations that they have. One is that they can make a maximum of 10 boats in a day, and another is that at least 2 more fiberglass boats than aluminum boats are made each day. So, in answer to A, just so we can understand this problem, it says, what are two possible combinations of aluminum and fiberglass boats that can be made in a day? So the limitations are that a maximum of 10 boats can be made, and there's always at least 2 more fiberglass boats than aluminum boats. So there's plenty of combinations here that would exist. One might be, for example, 7 fiberglass boats and 3 aluminum boats. That would be at least 2 more fiberglass boats and a maximum of 10 boats in a day. Another possibility might be 5 fiberglass boats and 2 aluminum boats. That's a maximum, that's less than 10 boats in a day, and that's at least 2 more fiberglass boats than aluminum boats. So there are lots and lots and lots of possible combinations to represent this. Our goal is to be able to represent all the possible combinations on a graph or a set of coordinate planes. Part B here says, define the variables and label the axes. So I've already defined the variables. What we're looking at here, and the relationship that we're looking at is the number of fiberglass boats and the number of aluminum boats. So if I was to represent that, I would do this. I'm going to label the x-axis with an A, which is aluminum boats, and the y-axis with an F, which is fiberglass boats. So that's kind of the representation as far as labeling it goes. Now the next part says, write a system of linear inequalities that represent the constraints of the possible combination of aluminum and fiberglass boats that can be made each day. I'm going to actually skip that part for the moment. That's the more mathematical way to represent the solution, but I will show you that later on. Let's first of all look at the non-mathematical way. So I'm going to represent the solution set on the coordinate plane. So how can we represent on the coordinate plane all the possible combinations of fiberglass and aluminum boats that can be made in one day? And here's the non-mathematical way. What you do is you need boundary lines. So the boundary line for a maximum of 10 boats can be made in a day. If you take out the word maximum, the boundary would be when there are exactly 10 boats made in a day. So if we can find two combinations where there's exactly 10 boats made in a day, and there's lots of them, we'll have the boundary line. So here's an example of exactly 10 boats being made in a day. If I had 10 fiberglass and no aluminums, that would be exactly 10 boats in a day. Or another combination of exactly 10 boats in a day would be if there were 10 aluminum boats and no fiberglass boats. So that would be another possible combination that would represent that possibility. So that would be our boundary line. And the next thing we have to ask ourselves is that boundary line included in the solution or not included in the solution? So are they allowed to, in other words, make 10 boats in a day? If it says a maximum of 10 boats, then 10 boats is a possibility, so that boundary line will be included. So what I would do is draw that as a solid boundary line. The next thing to ask yourself is which side of that boundary line should I shade? So if it's a maximum of 10 boats in a day, what I would want to represent is possible combinations. So underneath that line represents less than 10 boats a day. So all of these combinations below that line are less than 10 boats a day. So what I would want to do is actually shade beneath that boundary line that represents exactly 10 boats in a day. So that would be my solution to my first limitation or constraint. So this would be it here. Okay. So that's kind of the big idea at this particular moment. Now we've got another set of constraints here. The second set of constraints says, and I'll go up there in 1 second, the second set of constraints says this. It says, there are at least 2 more fiberglass boats than aluminum boats. So if we take that word at least out, we'll have the boundary. So give me 2 possible combinations where there's exactly 2 more fiberglass boats than aluminum boats. And there's lots of possible combinations. So exactly 2 more fiberglass boats than aluminum boats. Here's a possible combination right here, because that would be no aluminum boats and 2 fiberglass boats. So that's exactly 2 more fiberglass boats than aluminum boats. Here's another point where there's exactly 2 more fiberglass boats than aluminum boats. There's 3 fiberglass boats and 1 aluminum boat. Or here's another one. As you can see, you only need 2 points. So the last thing to ask yourself about that boundary is it inclusive? Are you allowed to have exactly 2 more fiberglass boats than aluminum boats? And the answer to that is yes. If it's at least 2 more fiberglass boats, then you are allowed to have exactly 2 more fiberglass boats. So that particular point, or that particular boundary line, should be a solid boundary line because it's inclusive. Okay, so it would look something like this. The next thing to do is to figure out which side of that to shade. So which side of that line would have at least 2 more fiberglass boats than aluminum boats? So you want to ask yourself, for example, is this point here at least 2 more fiberglass boats than aluminum boats? This is 3 fiberglass and 4 aluminum. That is not at least 2 more fiberglass than aluminum. How about this point? That would be 6 fiberglass and 1 aluminum. Is that at least 2 more fiberglass than aluminum? Yes. So what that means is that that side of the boundary line, which is above it here, would be shaded. Okay, would represent solutions to that constraint. I've intentionally used these 2 colors, blue and yellow, because what you're noticing here is that when they overlap each other, you're getting a light green color, and that represents our solution set. So where are all the solutions here? Well, the last thing to do is actually recognize. So the solutions are represented in this green overlapping area, but we need to recognize that you cannot sell or make negative boats. So we'd also want to get rid of these quadrants because you can't have negatives. We'd also only want to include the integer value combinations. So these are the only possible combinations of boats that can be made in a day, just the integers. That's why I'm drawing dots here, and I'll mention that when we talk about the restrictions in just a little bit. So if you notice, what you will notice is the 2 combinations that we came up initially in part A, 7 fiberglass and 3 aluminums, that will be in the solution set. That's right here. Sorry, right here, 7 fiberglass and 3 aluminums. Or 5 fiberglass and 2 aluminums, that's this point right here. So these are all the possible combinations, and these are the only combinations of boats that that particular company can make. Now, if you would like to do this the mathematical way, here's what the constraints would look like. So a maximum of 10 boats can be made in a day. It would look like this. A maximum of 10 boats made in a day would look like the aluminums plus the fiberglass have to be less than or equal to 10 boats. That would be a maximum of 10. So they're less than or equal to 10. And if you'd like to graph that boundary line, I can show you right here. Sorry about the orange part, that shouldn't be showing yet, but the boundary line would just be where f plus a equals 10. So if you substitute a equals 0, you get f equals 10. That's the point that we already have on the boundary line. Or f equals 0, we get a equals 10. And we have this point on the boundary line. And we could graph the boundary, use a test point of 0, 0. So we'd ask ourselves, is 0 plus 0 less than or equal to 10? And we would have shaded below it. So we would have gotten the exact same blue inequality that I have represented there. And the second constraint, which would be at least 2 more fiberglass boats than aluminum boats, would look like this. Fiberglass boats are greater than or equal to aluminum plus 2. They're at least, so they're more than, they're at least 2 more than the aluminum boats. So, and if you want to use your boundary line with that, the mathematical way, when you substitute 0 in for a, you get f equals 2, which is this point here. And when you substitute 0 in for f, you would have 0 equals a plus 2, subtract 2, and you have a equals negative 2, which is this point here. So these are the 2 points you'd have on your boundary line. And using your test point, you would find that you shade the opposite side of 0, 0, because you get a no. So you can look at this and pause it if you'd like to, but you would come up with the exact same graph here representing our solution set. And the last part here is, are there any restrictions on the variable? As we already know, we can only build positive integer boats. So that means, in other words, we're restricted to whole numbers. Okay, that's why I crossed out the negative quadrants and put integers in this overlapping part. We're going to look at one more example and then we'll stop this lesson for today. Problem 2 is not a word problem, but it's just asking us to understand inequalities in a different way. It says, without representing the solution set on a coordinate plane, determine if each point is a possible solution to the set. So we've got two sets of constraints, or two inequalities here, and we're asked, is the point 0, 0 a solution? So really what we're asking is 0, 0 a solution to both inequalities? So I could just use that as a test point. So what you're asking yourself is 3 times 0, so 3 times x minus 6 times y, minus 6 times 0, less than 18. Well, if we evaluate the left-hand side, that would be 0. Is 0 less than 18? Your answer here is yes. Okay. However, it has to satisfy, this point needs to be a yes in both inequalities. So the next thing we ask ourselves is 0, is x, greater than or equal to negative 3? So is 0 greater than or equal to negative 3? And the answer to that is yes. So the answer to the big question is this point a solution? It would be yes. Okay. Next would be, is negative 4, 3 a solution? So you're asking yourself for the first inequality, is 3 times x, 3 times negative 4, minus 6 times y, 6 times 3, less than 18. If we evaluate that, we'll get, is negative 12 minus 18 less than 18? Or is negative 30 less than 18? The answer to that would be yes. However, we need to check the other inequality, which says, is x greater than or equal to negative 3? X is negative 4. So you're asking yourself, is negative 4 greater than or equal to negative 3? The answer to there is no, because for negative numbers, the smaller the negative value, the actual larger it is. So negative 3, if you're looking at a number line, is actually larger than negative 4. Negative 4 is less than. So your answer here is no, which means that your answer to the original question is no, because they both have to work. The last problem is actually specifically looking at the restrictions. If you look here, it says for both inequalities that they must belong to integers. So you don't even need to check this point, because 0.5 and 1.5 are not integers. So since they are not integers, your answer is no.